All right. Thank you all for attending this lecture. It's a pleasure to introduce Professor Francesco Sannino, Professor of Theoretical Physics, Head of the CV3 Research Group, Co-Director of DIAS. And if I went into all the details, I could spend the entire lecture on that. Instead, I will give the word to Francesco.
Thanks. So, first of all, thanks for coming, for sparing your time and sometimes your lunch. To give lectures like this is very hard because it needs to appeal to many people with many different backgrounds. So, I promise there won't be many questions, maybe only 3. That will be very unorthodox, and also should appeal also to the theoretical physicists. So, it'll be also something that they can also gain out of that, or actually like to the mathematicians, maybe also to other people. And it's really about the laws of the universe. So, what are the basic principles behind that, and why they're elegant. Right? So we don't really appreciate that. Because nature is elegant. It's all about beauty. First I want to say, before I forget, thank you to all the, as a theoretical physics, or a theoretical physicist, I basically been blessed with outstanding young people that work with me and collaborators. All the CP3 group, but even before that, these are always extremely bright kids that give their life. And then you deserve a little bit of spotlight for them. I think this is really, I always enjoyed working with them and learning from them. So now let's go back to the universe. Now, let's start with the story of the universe, right? Let's put a little bit in perspective. So if you were to think about the universe and think how old it is, and I know people work on demography and you would like to know how old is the universe, but you don't really have a principle to actually comprehend that. If we can give you a number, billions of years, what does it mean for you? It's a number, right? So what? So I like this to actually put on a cosmic calendar. Right? If the entire history of the universe would be put in 1 year, where today is the last day, the 31st of December, when these things happen, that should help you put things in perspective. At me, okay? Actually, on day 1, on January 1st, the universe was born, and almost is expanded as big as it is today, and almost no time. That's called cosmic inflation. We don't know if that principle is true. We know that it solves a number of problems, right? Like what? Right? If somebody had made us, you will know it. How? You look at the sky. And if somebody made you, you would have left an imprint. I am God, and I made you. So you look at the statistics in the sky, and you find out the sky is actually not telling you anything. Then you can keep believing in God if you want to. I stop doing that if I can't see that. As if I were Armani, I would like to, this is saying, but I did it by saying. Right? Good. Then the Milky Way, the galaxy that hosts us, appeared in March. Now, here to help you, each month is roughly 1 billion years. Each day is about 38 million years, and each minute is 26,000 years. So that's pretty cool, I love that. In August, the sun appeared. August last year, you were actually testing the sun. I can see you smiling because it relates to you, right? More than a billion years. The first known species, and again, I don't take any credit for that, to be very clear, right? So I could be wrong if the person made that made it wrong. But I think roughly made sense to me. But 3.5 billion years ago, we had the first known life appearances. They help making oxygen, and I think there is a world expert here, Don Kempfert, that works on that. That actually started about 2.3 billion years ago, in October, this year. In November, we start having the first complex cells, so biology starts really kicking. So you have to wait till November, actually, to do something. I left the best for last, which is December, right? You need to, appreciate December. December is, nothing happens very much till the 14th of December, where the first animals start appearing. But December was really dull until the very, very last factor. On the 17th, fishes. On the 20th, land plants. Insect on the 21st, so zoology starts, kicking up, right? And then all kind of reptiles, dinosaurs on the 25th of December. Then we lost them on the 30th of December. So they lasted 4 days on the cosmic calendar. Poor people, poor reptiles. On the 31st of December, a number of things happened. Now I'll go by the time. At 6:12 a.m., first apes appear. Right? So that's on the morning of the 31st of December. At 9:11 p.m., so we need to wait almost the end of the day to start differentiating apes from humanoids. Humans and chimps did roughly diverged around 9:11 p.m. Around 11:52, which is basically now less than half an hour ago, yeah? You started having the anatomically modern human. I guess medicine probably studied that, right? The pyramids appeared at 23:59 and 49 seconds from basically almost now. The Great Pyramid of Gaza. Columbus found the America just 1 second before midnight. The rest is history. After the discovery of the US and America, we just move on with that Trump, and that's it. That would probably be the end of the species too. That's the full cycle. Now, this should actually at least put me, in a position to now relate to you, right? Because you have at least a timeline in your brain. And I think it's good to have a human timeline. 1 year you can comprehend. Now, what is physics? What is theoretical physics? We're not interested in the last 1 second. We're interested in the complete history. You can admit that's pretty cool. If you don't, I really don't understand. I can really be allowed to research. That's a dream of any kid that wants to do physics, right? To understand this. I see some people there that work on cosmology. Yeah, that's true. And that's fun. That's a lot of fun. Now, this is the way physicists will draw exactly the same thing, which you will not understand a word that they're saying if I put this in. Right? Or at least you pretend to not, so of course I understand. This is the Big Bang. After that, so this is the size of our universe, okay? So you can see that our universe grew very much, almost instantaneously. Then different interactions took place at different epoch in our, which are all classified here in 10. So this is 0. This is 10 to the minus 36 seconds from the Big Bang, 10 to the minus 10, 10 to the minus 4. And here you see the experiments that currently are exploring the different times of the static of the universe. So the Large Hadron Collider is actually positioned at 10 to the minus 10 seconds from the Big Bang. That's pretty cool, right? Cosmic rays, which have been really the highest energy always, ever studied, always have worked at even higher energy than the Large Hadron Collider. Because these are rays at a very, very energy made by nature itself. Finally, if you want to study the plasma, so for SON, you go still at CERN, or previous was also the research on AVI and collision Brookhaven, and that they studied, for example, the plasma of dense matter. And eventually, at one point, the universe was cooling down, and all of this we can't see. I mean, we can reproduce it in experiments. What we can see in the sky, because as you know, by looking at the sky, you look at your own history. Right? The light that comes to you is from the past. That's the way you know that you passed. Right? So this is what basically covers all these things before, called also as cosmic microwave background radiation. And it was discovered by chance by two Bell physicists working for making telephones free. If you wanted applied science, right? But they couldn't ever get a signal very good. So they thought it was some bug in their instruments. Actually, the bug was not in the instruments, but the fact that this is the background radiation that you can never get rid of. And got a Nobel Prize for that. I mean, it's not too bad. Also a fundamental sum. Then the rest, I mean, after that, gravity allows you to create structures. And finally, today, about 10 to 9 years from the Big Bang, we're here. If you like more in energy scale, that's the units that high energy physicists use, which are gigaelectromoles. Just to get an idea, when you work at the level of biology, we're talking about electromoles, much less than that. Nuclear is megaelectromoles. High energy physics is from hundreds of gigaelectromoles and plus. Okay. And these numbers, physicists, in particular theoretical physicists, they have very much imprinted in their head. Fine. You heard that there are forces in the universe. Maybe what you don't appreciate is, or you're not really very hard to grasp, where do they come from? I mean, it's not that you wake up one morning and you actually make a force. But they come from beauty and elegance. And then mathematicians will start getting a bit excited about that, because mathematics is all about beauty. What physicists like is how to use their beauty and embed nature into that. Fine. So you know this, right? This is the famous Michelangelo David. Of course, what you appreciate is the plasticity of that. Michelangelo made this in such a way that you feel a little bit unease when you look at it. One leg is, less symmetric than the other. His one arm is on the back. So the beauty of the David of Michelangelo is not in his fact that it's a static beauty, it's fact it's a movement. And that is by using rigorous mathematical tricks that Michelangelo put in his hand. That's what actually creates the beauty of the Michelangelo's David. Like I was last 2 weeks ago in Firenze, and there is a copy of Michelangelo David in front of Palazzo Vecchio. And history is that, why Firenze commissioned that to Michelangelo? Because Firenze was a small town. They wanted to show that they were really counting. So they commissioned Michelangelo David because he defied the Golia, which was a big town in their head. And that's why Michelangelo David came about. It's not considered the most beautiful David. It's actually by Bernini considered the most beautiful. But this is considered the most powerful. Now, of course, I love Eminem. I'm a bit weird too. And this is actually the, I know how to read notes, I know how to play the piano. So I always love that. And what is beauty about that? It's of course again about the music. If you heard that, it's kind of rockish-like, right? But you see that all these notes, they repeat in a certain way. But again, what gives you the thrill is the breaking of the rhythm. Right? Nowadays, they're so savvy, the people that make music, that can actually time it in such a way that you get the hang of it. Right? That's called torment in your brain. One of that in the summer was a Spanish song that played all along. You just could dance on the beat of it. What was the name of it? Which was? Despacito. Despacito, yeah, exactly. I mean, you could get, you hated it, but you danced to it. Right. And that's because they knew how to get to you. There are tricks when you compose that they teach you how I can manipulate your feelings using math. Isn't it great? That's the universe. What does it have in common with the other two? Let's look at that. And this I learned from the music school at Yale, right? So I'm playing the piano, I love to hear about that. So if you look at this picture, you feel very relaxed. It's a perfect circle. This picture is the best you can possibly imagine. You drink your cup of wine in front of that and you feel very, very unstressed. Now do something which is really evil. I delete one piece of that. Your brain is not going to rest. You start getting very stressed. Your brain mentally constantly tries to delete it. Dynamics actually comes from breaking the simple. breaking the symmetry is the fundamental principle behind any force of nature. And that's the beauty of it. I can make it more complicated, immensely more complicated, but you will not appreciate it. Now, for example, the photon. Where the photon comes from? The photon, is the quanta that mediates light. Anybody that works in photonics, they should know this. Right? If you don't, I'll be very stressed. Now, this is a wave function for a single electron on a 5-dimensional atomic orbital of a hydrogen atom. Basically, it tells you where the electron is. What's the probability for electron being around a hydrogen atom? People were saying cold atoms like this stuff a lot. So you learn that you have to have a wave function. Now I give up in quantum mechanics about telling you exactly where's the position and the location of the particle. I tell you the probability you can find it. It's actually a very natural concept, right? This probability, however, needs to come in square of a wave function. This is the probability psi bar times psi, so it's the complex conjugated times time in a given volume. This is the probability to find the electron in that infinitesimal volume. A very simple thing. One thing that is less known is that since this is psi star psi, if I multiply psi by a phase, and I assume all of you can do that. If you don't know what the phase is, I feel very stressed. So this is actually, I multiply this wave function by just a phase. If this phase is constant, then I'm perfectly fine. Probability, a conservation probability, because one thing I need to be sure that the electron will be there with unit probability, one integrated over the entire volume of space, right? I mean, I will have to have it. Otherwise, I don't have one electron. It comes from a symmetry principle. The symmetry associated with the conservation of this phase, which can be mapped into a circle, for the mathematician, that should be very simple, right? I mean, you go on an angle, after 2 pi, you go back to the same thing, right? So that's a circle. Now I do it and this was all you need to do in quantum mechanics. Now I do in a natural act. I say, at each point of space-time, make this angle depend on the space-time point. Is that the theory still in mind? And the answer is no. Because, for example, if I want to know the rate of change of the electron motion, I will have to act with the derivative. I need to differentiate. And when I differentiate, I start feeling that the angle is there. Right? So I need to compensate for it. How do I compensate for it? Mathematicians knew that since a long time ago. What they do is to redefine the derivative. That's known as covariant derivative. If you like fiber bundles, which I cite as a differential geometer, not as a physicist, in theoretical physics. That is a section of a fiber bundle where the bundle is the space-time and the fiber is called U1. Now, this is the compensator for this space-time dependent angle or circle. All and behold, this one is a principle of nature. We can prove it. It's just it's the photon. So the photon comes about by requiring a symmetry. By breaking the symmetry, which was just a global circle, into something that depends in each point of space-time, and by compensating for it. So interaction comes exactly with the same principle for which you want the David of Michelangelo to be beautiful. That is something like, I mean, if it doesn't strike you, I don't know what it should strike you. Anything that works on your iPhone comes from this. Isn't it correct? Any chemistry? Just that. Nothing else. Come on, Jesus. Now, that's what we call fundamental stuff, right? We stop there and then you guys take over and do a lot of very interesting stuff. I would share with me this discovery because it's a bit of a Nobel Prize discovery. Now, this is what I do, which I don't pretend to explain it today. This is actually my handwriting of a theory that I discovered recently. Go back to it. And you can see, if I would present that to you, you will be, leaving the room instantaneously. This guy is insane. Good. Are you still with me? So now we use the word fundamental interactions. So far I told you the forces. What does it mean fundamental? Because it's often abused. We say we do fundamental science, but nobody really explains what fundamental is. So that really stresses me. as a rigorous person, you need to tell me what you're doing and what actually means any adjective you're using. Please do that. Right? Because we confuse things every day, in everyday life. I don't understand. So, a more romantic way of saying is a passion for truth and beauty. A more specific way of saying is that a theory is fundamental, which means I'm really facing my God. If the theory is true at every possible energy scale, which means I'm putting myself out of business. Once I discovered the theory of everything, you can just close physics, will all be applied. Correct. No, Martin, we are very far away from that. Just in case you have bad ideas. Right. So now I did that with time. Now I'm going to do with length. So if you ask how big the universe is, right? It's also something to know. It's about 10 to 27 meters, which is an immense amount. Around 10 to the 21 meters, which is 7 orders of magnitude smaller than the visible universe, you will get the galaxies. Around 1 meters, you get me and my daughter, which is basically the size of humans. At about 10 to minus 11 meters, you start having atoms. You can do cold atoms and so on. Around the larger than collider energy scale, which again, when we talk about energy scale, the inverse of energy scale is actually distance. Inverse in particle physics and natural units. That tells you at which length scales the larger than collider operates. Now, the thing is that it's typically unappreciated that these and these are related. That's what typically happens in the sense. So the micro and the macro are actually very much related. Unless you understand one, you cannot understand the other. At even shorter scales, we have a so-called unknown territory. And around 10 to minus 35 meters, you can no longer forget about gravity being quantized. So that is actually the energy scale, the length scales that we operate. And we operate on all of them. That's what CPT does. I think this is insanely cool. Yes, it's very hard to explain to our press office that they love to discuss dinosaurs because it's easy to discuss dinosaurs. But this is cooler than dinosaurs. Now, if you look about the universe, you ask about what we're made of, and 5%, all I told you that we understand is about 5% of the universe. So we can understand the history of the universe because we can run backwards the movie. So I can actually make an accurate time movie. But if I tell you what we're made of, I can also tell you that. But I can also tell you that what makes us and what makes the stars is only 5% of the entire budget of the universe. So the other 95% you know what you can do. Imagine how much more chemistry you could do if you understand the other 95. That'd be cool, right? So, QED holds atoms together. And this is actually what the photon. But then something I didn't tell you is that you also are made of protons and neutrons, and protons are held together by another force called strong dynamics. Then there's a third force, the one which allows the sun to burn, which we call weak interactions. And thank God it's weak because we wouldn't exist if the sun would have born in August and ended in November. So we need to have it around for several months of the year to actually keep it. And that's the weak force that regulates the time. Now, how do these fundamental particles talk to each other? This is a very nice, actually accurate chart of how, at the very basic level, different particles that constitute our standard model work with each other. For example, the photon sees the electrons, so this electrons means electrons and electrons, basically. He sees the W, he sees the Z, these are all quanta. The W and the Z carries weak interactions. The glue carries strong dynamics. Remember, I told you need the photon for getting electrodynamic interactions. The W and the Z carry the weak interactions, and the glues carry strong dynamics. That's why they're on display. The photon never really talks to each other, to themselves. They talk only to objects that carry electric charge. So they talk to the W, but it doesn't talk with the Z here. The W can talk to itself. The Z can talk with the leptons, but it cannot talk with the photons. The glue can talk to itself, can talk with the quarks, and quarks are seen by the photons, are seen by the W, seen by the Z. And finally, the Higgs can talk to itself. This part has not been studied yet at the Large Hadron Collider. So see, I can actually go for hours on this. Hours and hours and hours, because this is a 3-level interaction, and higher order interactions, that's what we do for you. The Higgs, however, will talk to all the others, to the leptons, to the W, to the Z, to the quarks, but not directly with the photon, and not directly with the glue, even though in a kind of paradoxical way, the Higgs has been seen through the photons. Because through the interaction with the leptons, they also see the photon. Make sense? This is some theoretical physicists call this the moose diagram, because it looks like mooses on the head of some deers, okay? Fine. Of course, you have heard about CERN, but you of course know that there have been collisions, and many of them changed the history of science forever. Right? One famous one was the Hubble head on the head of Newton. So I was in Cambridge in Mali for a few weeks, and then Hugh, a very Osborne, a famous professor in Cambridge, which works one of our postdoc here, this colleague, he brought me. I was staying in the Fellow Lodge, which is fantastic, beautiful place, and then showed, you see that room up there? That's Newton. And then in a very huge way, he said, he was nice. Being a British person, I mean, he was really great in the way he said. And of course, we also had another collider which made, for example, the Higgs. They're equally landmarks in history of science. For example, this was the day where the Higgs was announced at CERN. It was reported by the New York Times. You can see they took a long time for the Higgs to be discovered. They're all very old. Luciano Maiani, Professor Rome, was the head of CERN before the last two directors. Very good. And these are the two young chaps. They got a Nobel Prize for the Higgs. This actually is the Higgs. Peter, also known as Peter the Higgs. And this is Francois Engler. They hated the guts of each other. Really. Mostly because Francois, we always call it the Higgs, we don't call it the Engler. So if you go in Belgium, where Chris has been in his group, right? Can you say it's the Higgs boson?
No.
No. How do you have to call it?
Either you have to say Brute, Engler, Higgs, or you say the scalar.
It's the only place on earth where you have to do that. Yes, that's okay. And in fact, none of the two gave this name to this particular particle. It was given by Steve Weinberg, which actually was at the talk and understood how that worked. And they were also pretty likely that these other guys had helped discover the mechanism, and Keeble discovered this mechanism in condensed matter. So high energy physicists really backpicked on the condensed matter physicists. Sometimes we do that too. That's as C. Jobs says, great inventors steal. They stole and stole in a cool way, made it relativistic, and applied it for fundamental interactions. So they were likely that these people died in the process, but before they discovered, otherwise they couldn't get it. And also the history behind the Higgs is that in the first version of the paper that Peter said, the Higgs wasn't really there as a part. It was a fantastic referee. Now what's been talked about this matter referee, which got a Nobel Prize actually of Japanese origin, Nambu, which was also the advisor of my advisor, one advisor of my American advisor. Nambu said, oh, okay, but this is nothing new unless you put a new scalar in that. Okay, I'll do it. And he thanks in a footnote Nambu. He didn't know it was Nambu. So sometimes, please be outstanding referees, but be smart. Don't make stupid comments. So they can give a Nobel Prize to the person who is applying or sending an application. Fine. Now this is a real time. You will see a little animation. You see this little bump here is the Higgs. This is the Higgs decay into two photons. Two loop corrections or quantum corrections, which were not thought to be easy to be seen at the Large Hadron Collider. Okay, so they had to learn how to do statistics. We discussed statistics today to be able to subtract the background here and actually make the Higgs. And let's see if this works. This is accumulating in time statistics. till actually this happens. And now you see the Higgs appearing. Also in another process, H to Z star. Star means into one is virtual, and this is the fault. Each of them at that time could not have been considered as a discovery of the Higgs. But combining statistics of these two, you were actually above the 5 sigma. Now, in high energy physics, we're pretty damn harsh on statistics. I mean, in other fields, 3 sigma or and a half, it's okay. In us, at the large enough collage, unless you're 5 sigma and above, nobody even listens. So it's really, really tough. The screening is really, really tough. Because if you wouldn't do that, by now they would have probably announced so many discoveries. I mean, we hear things and rumors and disappear so quickly because you need to be very careful. Make sense? Again, I don't pretend you to actually understand specifically these plots, but you should feel the excitement, right? When these things popped up, wasn't too bad. And of course, that's the way the press sees that, right? We have discovered what nothingness is made of. Oh, it's quite something. And this is actually the exciting ones. Can anybody spot, except for the 63 people, 2 Nobel Prizes in here? Yes! And the Higgs. Right. So there were 2. So after the Higgs, times are changing. So why we're so excited, what is interesting in that? So at CERN, currently the largest collider there is, we seem to see that the standard model works, but they're still asking whether it's actually the ultimate discovery. The fact that you've seen something doesn't mean that's the only thing. In fact, maybe it's the Higgs much more than that. So is the Higgs alone? Well, new particles come in. Are there new forces? Why 4? Well, why not 10? Right? It's not man given the number of forces we have. And it will actually motivate the new forces must exist to understand the other 95% of the universe. Is this the right energy scale for new stuff? Do we actually have a glimpse of dark matter? And as I said before, a theory is fundamentally, if valid at any energy scale, the standard model is not. We know breaks down mathematically. So it can be an ultimate nature. Now, if you're more mathematical, you will say that the same sentence that I said it in words, that the theory must be true at that energy scale, requires so-called short distance conformality. I will actually a little move what conformality really means, so we can try that. So for you now, this is basically Chinese. I apologize for the Chinese, but to them it's Chinese. Good. So effectively, the Higgs is a kind of a matryoshka. So now we've discovered something. What else can you discover? Well, why searching for something else? You're done. Oh, right. We hear that. That's basic ignorance. Very, very loudly. Because the standard model has no dark matter, it predicts the wrong dark energy. So according to the standard model, we wouldn't exist. Then it must be wrong. The standard model does not give mass to the neutrinos. Somebody here works with neutrinos, likes that too. At least it's not, certainly not the Mobius zone. In fact, our universe is not even stable according to the standard model. Wouldn't you like to be in a stable universe? Of course, you might not want to pay your taxes, but I wouldn't do that. I would pay the taxes. And even wrong, we say there's 5% matter, and you get it wrong now. But actually, it works for many other reasons. So there is a dichotomy there. You need to do something. Again, each of these subjects, it takes a graduate school of 10 weeks to go through it, and there'll be hundreds of papers, thousands of papers. So excuse me if I don't go more in detail on that. Right? And above all, we can't even have inflation, which we cannot make even a universe as far. Okay, so it's a great triumph for so far, but we can do better. So unfortunately, you guys have to have us around for a bit long. And certainly, you can prove mathematically it's not a fundamental theory. Means that I write down the equation and demonstrate that this standard model doesn't stand on its own, which is cool. And least but not the last, quantum gravity. I never really spoke about quantum gravity. I'm being very smart and not touching very, very hot, issues, right? Problematic issues. Quantum gravity, that's okay. But it is, having discovered something, it's now a window for something new, right? Every time you discover something, you can use it to explore something else. So it's a window on the micro and macro universe. And it's being used for that. Good. For example, what I work on, I don't pretend you to understand everything, but if the Higgs is made of something else, this would be the Higgs you see, for example, the Larger Than Collider, but actually it's made of this stuff, called Technique Works and Anti-Technique Works. This is a paper that was published in the Journal of Energy Physics a year and a half ago. And it's the first working theory also called Composite Dynamics, which means this object, the Higgs, is truly made of something else. And when you say it's made of something else, it implies a number of consequences, a number of predictions that you can actually test. That's pretty cool, isn't it? Because mingling with theories of nature is pretty fun. Making it works is even better. Agrees with experiments, predicts new exciting particles. Somebody here, no, Anna said to go back to teach, working on that. Made immense progress. And you have new phenomena to be studied, both with high-performance computing and understanding the theories, new theories in fundamental interactions, and actually even press seems to like it. So it was actually featured in different journals. And I think it's cooler than 9 years, because this could be a new theory of nature. Maybe it won't be, but I'm excited about that. Good. Now the mysteries. I already presented many of that. Well, let's go very quickly through the mysteries again. Right? So I actually, when I was a kid, I was watching the X-Files. And of course you get the thrill when you see the X-Files. And you should feel the same thrill when you think about the universe, right? And I think it's more exciting than the X-Files. And how do you discover these thrills, right? You need some investigators. What are the investigators for us? Of course, are the experiments, right? Because we're thrilled about the theory, but we're even more thrilled about what the experiment tells us. But how do we do energy physics? How do you make new stuff? Well, you can make it on Earth by building large, colliders, very energetic colliders. You can wait in the sky by looking at cosmic rays, because are already colliders in the sky. But you can do something else. You can actually scan the sky and do cosmology. All these are related. Or you can wait on Earth. So you have experiments that are underground, waiting for dark matter to hit them. That's pretty cool. And I can show that all the physics, from dark matter to astrophysics, Higgs sector and cosmology, are related. Higgs can be used for inflating the universe if we were the right Higgs, if we were at the right scale. Man, I would love to see that. Now, this also tells you how complicated it is for these kids, when they do theoretical physics, to become a theoretical physicist. The amount of whipping they get to actually put that in their mind is not, is not little. I feel for them. It's actually very hard, and they know that. But they give all the best they've got. But as Feynman said, you can have your theory, but if you disagree with the experiment, throw it out to start from scratch. And that happens more often than not, because we know that only one theory is right. So we are definitely sure that 99.99% of all the theory out there cannot be right. Eventually one will hit the jackpot. That's life. So you should be also humble enough to know that I'm definitely working on the wrong one, but at least should be the wrong one that is, has got the best shot. Make sense? And that also requires taste in picking up your theories. The first mystery I already mentioned before. I mean, till 15 years ago, you could have said, well, okay, atoms that makes the universe, make the stars. Would be great. Already have all the standard modelers points a lot of that. And then you start having the dark matter should be that. That makes 27% of the universe. And then dark energy makes the other 68%. And this, we didn't see it coming. Till experiments. Because of course, humans are very pretentious, right? You think you have an idea, and often you think that explains everything. That's the whole, in physics, the spherical tau approximation. You take the legs away, you take the head away, and first approximation is tau, the tau is field. And then you start putting the legs and so forth, and things not really fit. So this is a big mystery, right? When you agree that not knowing 95% of the universe is bad, or it's actually insane, you live in it. The other thing which actually should feel you very unsettled, if this wouldn't be there, our galaxy will not actually be formed yet. So you wouldn't be here. So when people say I want to understand life on Earth, human being and life are without a So don't you think it's a fundamental question to ask? I think it is. And many people do that. Fine. Then there's a puzzle of three. And this is a purely theoretical puzzle. Okay? Why is it that? Well, there's the electron. I will love it because it makes the atom. Like if you ask Sebastian, without electrons, you probably wouldn't be able to do much. Maybe you need also the proton and the neutron. That's okay. But then you have the neutrino, this is a companion of the electron, which allows the thermonuclear reaction of the sun. So good. And then you have another coupling, a muon. Maybe one day you can make another atom muon, so people actually do that, because it will make the atom more compacted. And that's great too, right? And then you have the tau. But who the hell sent them? Right? Why would nature send you 3 copies of the same stuff, just a little bit heavier? Right? As somebody said, I don't remember the name. Okay, we got the electron, but who has ordered the muon? Right? It wasn't on our dish. We didn't pay for it. So we have no clue why that's the case. And then the story repeats for quarks. There's an up and down, a charm is strange, and top and bottom. And then each of them comes in 3 different colors. Then you have 3 different forces. I'm not, I'm standing clear from gravity. The force for the strong dynamics that holds the quarks inside the proton, the electromagnetic force, and the weak force, which made by weak forces. So let me say, like the puzzle of 3 families, 3 colors, 3 forces. If you have a good idea in solving that, but you should write your own PRL paper and not let me see before you start. Because if you explain it, typically it means also the predictions. You can also predict move around their physics, perhaps even the right type of Dagmar. And you can get another prize, I can guarantee you. Now, perhaps can a sphere help? Right? I promised you something fun. Oh, this works. Now, this mathematician should love, and slide is disconnected, but you will get back to it. Oh, sorry.
Mobius transformations are among the most fundamental mappings in geometry, with applications from brane mapping to relativity theory. A Mobius transformation sends each point on the plane to a corresponding point. They're built from 4 basic types. The simple translations, dilations,
Don't fall asleep.
rotations, and inversions, which turn the plane inside out. Lines on the plane either remain lines or transform to circles, and right angles stay true. In general, a Mobius transformation can be a complicated combination of all 4 effects. The true unity of Mobius transformations is revealed by moving into the next dimension. Taking a cue from Bernard Riemann, we place a sphere above the plane. A light at the top shines through the spherical surface, illuminating the plane. As the sphere moves, the points on the plane follow. When the sphere translates, so does the plane. Raising the sphere gives dilation. Spin the sphere like a top, and the plane rotates. Rotation about a horizontal axis corresponds to inversion. Even the most complicated Mobius transformations are revealed to be simple motions of the sphere.
Okay. So, I was scratching my head to tell you what conformal transformations were, and I found this video and I thought I couldn't see that. Now, remember I said if you have a symmetry, which is a circle, I can get a photo. You get even more symmetries. Imagine what you can do. Conformal invariance, or invariance under scale, or all the other symmetries here, is a fundamental principle that allows us to actually classify our theorems. So I can use that principle of symmetry under conformality to define theories of fundamental. That's what I do. That's what Thomas is doing. And to the left-hand side, you have the famous Escher, a Dutch graphic artist that used mathematics to make his drawings, his famous drawing. And it was in the 80s, a famous book, Bach, Escher, and Fischer, about the famous principle of mathematics. I read since I was a kid. It's pretty tough book, but it's interesting. And this is a picture of him. Now, this is exactly what you showed before in terms of conformality, right? How you can transform the lines using a sphere. If you have, now I will call conformal invariance, that ensures fundamentality. I will not argue why is that the case, but one very simple way to think about that is remember that there is a scale invariance, which means it doesn't depend on the distance. So clearly, if it doesn't depend on the distance, it got to be fundamental, but it doesn't depend on which distance you start, if the theory is invariant. One of the other byproducts of conformality is masslessness, which means your theory does not have masses. And for large good approximations, we actually, if we compare it to the energy scale of gravity, our particles are very light. Finally, it leaves a new way to unify forces. Oh, that's very cool. So this is the physicist's way of looking at that. So in the physics we say that there is an interaction strength, that for example, interaction strength that tells how different generalized quarks work, and this is how they talk, for example, to a Higgs. So this interaction strength tells you that at this point, the theory is conformal in the assured distances. So I recover this invariance. This means that this theory, along this red line, from low energy to high energy, is a fundamental theory, which means it's true at any energy scale. This theory is on a pedestal compared to other theories I can have. The standard model is not there. That's what I do. Now there are other things like irrelevant or relevant direction that basically defines for you the dimensionality of your fundamental interactions in terms of many couplings are really relevant. And this is something that I discovered maybe 2 years ago. As the first four-dimensional complete asymptotically safe quantum field theory, which means all the interaction, this theory as a skeleton looks like the standard model. It has not only gauge dynamics, it has an interaction with the Higgs, a generalized Higgs, and the self-interaction with the Higgs itself. And these ones have actually something that is pretty interesting, that all the couplings are actually related on the assured distance, and are predicted by the geometry of the theory. So this is actually unification in space. It also provides for you a scale that tells you what is high energy, what is low energy. So this is a different way to unify the forces, where the Higgs in this theory for the first time is a mass. You cannot do without it, just by pure mathematics. Right? So you don't have to search in experiments, you know that has to be there in this theory to be well-defined assured distances. Again, I don't want to dwell on that. But I'm almost toward the end of it. How do we actually, a theoretical physicist, find? I've been often asked the question, I mean, what do you do at the office? Right? You scratch your head and an idea comes up. I got this question. So let's see. It's very simple. You got the idea, then you actually look at the mathematical theory space. You check whether the theory is mathematically consistent. Don't waste your time on theory which are wrong. Right? Mathematically wrong. Then you go and make a model of that links to nature. And then if your model is very complicated, you will need, for example, somebody like Claudio to actually look on a supercomputer the dynamics of this theory. Or if you're like it, this is sufficient to be a manageable theory to do more or less by pen and paper the link to the experiments. Sometimes you need some computing, but sometimes you actually can practice. Most often than not, you will need some extra tools. For example, Claudio, and sorry, Heidi, Jack, she actually develops these tools to connect it to the Large Hadron Collider. Because Large Hadron Collider is, two elephants colliding with each other, right? From having a fundamental theory to predicting to elephants do is pretty complex. So she will have to study that. And then you go back and say, well, it wasn't actually completely correct, let's go back to it and start again. That's the way it works. Clearly it's highly interdisciplinary, right? Because from math to the way you think about that, to the experiments, I mean, good luck. So it's pretty fun. That's what we do here. And for example, CP3, the theory space and math consistency is what we have in one part of our CP3 unit, which is theoretical and high energy physics and cosmology. Then we have dark and bright phenomenology, that what actually take the theories and link it to experiments. And then we have the lattice for beyond fundamental physics, a more general lattice that studies and uses this theory on hyperforms to actually test whether the dynamics is correct and predictions for what experiments do. Make sense? Good. Fine. So how am I doing? 1 more minute? Whatever.
10.
Ah, fantastic. Fantastic. You got it. Now, you shouldn't leave this room without feeling the taste of new physics, right? So let's see. Is there any new physics coming up? I cannot promise, you'll see that. And it's insanely cool stuff, right? As some of you know, I've been at CERN for about 6 months last year as a scientific associate, and been extremely productive, as it is here too. It was fun there too. And while I was there, in April, 2 days, on Monday after Easter, they announced some results, the Large Hadron Collider beauty collaboration. So a small but persistent discrepancy between the rates at which particles called beam essence. So again, that sounds to you not very much neither English nor Danish. They came to different pairs of leptons as physicists in theory. Now we knew, started getting these ideas 10 days before, which meant that really was over Easter, right? Because there is this bad habit of the experimental collaboration at CERN to give the good news or the bad news the day after some holiday, because they need to rehearse what they're doing. They ruin also their holidays, but they make the love of tears insane. And I was supposed to visit my mother in North Italy with my family the day came, so we had that. So 5 of us started thinking about that. And I can just say that this led to one of the papers in the field, which were 6 papers on the same day, or the day after they announced the thing, because we actually worked on that very intensely. I went to my mother, didn't see for 2 years. And I go say, I'm sorry, do you have a room where I can go? It's only my bedroom. That's fine, go. Always you. You can enjoy the kids, the grandkids. So in fact, I will dedicate this to the penguin that stole my Easter egg. Why the penguin? Because the diagrams, the so-called Feynman diagrams, which are involved in this kind of physics, are called penguin diagrams. And it was a bet by one of the physicists in the 80s, John Ellis, that he could put the word penguin in one of his papers. And I had to also justify. They were actually high. I'm sure John knows. So they actually, they were. I'm pretty sure of that. So that's actually the diagram. The big quark comes in, transforms itself into something, and then it goes to a strange quark, and then it's other quarks here coming around, and then you have 2 leptons. That's why it's called lepton. And something else goes here. So the question is, a new physics could hide into these diagrams, okay, if you're not a star model. Now, the experiment, so we didn't know by how much. This is all these blue, green, red, and violet are the theoretical prediction from the standard model. They asked 4 different independent groups before putting the paper out, these experimentalists. Tell us your best prediction for the standard model. And then they came up with what they get, and it took 2 years to do the analysis. Now these guys are damn serious. And if in fact they screwed up, some heads are going to roll. So, but they stick their neck out. So they actually, you can see there is an obvious discrepancy between these. Okay? So what that's due to? So we wrote this paper. This is probably one of the few more authors on that, because we need also cosmologists. Why cosmologists? Because I just showed these 2 data, but actually if you want to do this professionally, you have to test with respect to many other observables, hundreds of other observables. So the statistics of that had to be done extremely well, and we needed people that know how to do this with cosmic microwave background, which is Guido D'Amico. I don't want to get, but we had a lot of fun. And nice enough, I mean, two of the postdocs which are at CERN now were CP3 people before, right? They moved from, Marco was our actually first postdoc at CP3, then he moved to Cambridge, then after Cambridge moved to CERN, and now he has a permanent job at the Scuola Avanzata Superiore in Trieste. And Paolo is actually from CERN, and he's younger than Marco. So there were three people from CP3, and then people from CERN, people from, let's produce nerd. And what you discover, indeed, is that the standard model is outside the band. If you yeah, so I'm almost there. So, alone is not yet enough to say that this is a new physics. However, if you include all the observables, the clean observables, the ones that cannot be contaminated by any other kind of theoretical or experimental potential mistake, you go up to 4 sigma. It's not yet a discovery, but it's pretty damn good. I mean, if you actually do the numbers, 4 sigma is 99%. So we're not at 99.9. And if you also include dirty, in the published version, we had to eliminate the word dirty. Because some of the referees were the people that invented dirty. So we need to have to call them others. Other observables, you actually go up to 7 sigma. That's not too bad. Other 5 papers, 4 papers came after the same day as us, all agreeing with our result. This paper, after a few months, stops out. So it's a landmark in the science. It's pretty cool. If true, so imagine now, entertain the possibility that indeed this is actually an actual result. Again, the theories cannot be wrong. The experimental is good. If that's the case, then a new particle could actually emerge at Z prime. So now this is a Feynman diagram where you have a Z prime here. Or you could have a leptoquark. So in the model, for example, I showed you in my model where you have the Higgs made of something else, these leptoquarks are automatically there. So it's pretty cool. So it can be scalar leptoquark, can be vector leptoquark, and I don't want to get into the details of that. It can come from partial compositeness, exactly the model I told you. Now you can see that this leptoquark can be seen as made out of this box. It's composite. And it also has other effect on other physics that you would like to see. Because once you make a new model, the consistency of that is, if you do a model that fits one experiment, most likely, it's always true that you're also going to screw up something else. And you predict something else. That's the power of science. So you cannot escape the inevitable consequences of your own theory. And that's the fun part. I would say that we have to keep calm and wait for more data that will come very soon. I can't promise that this will remain, but if it remains, it will be a little bit of, it will not be a little bit, it will be a revolution. This is fun. I'm pretty cool about that. Things have gone away in the past, they won't go away again. But we as theorists need to be ready for that. We need to be the first one to write it. CP3 needs to be the first one to write it. Hey, you guys know that. Good. On my list. So this is actually technically the last slide. What I want to do personally. I think that the only way you can make progress besides experiment as a theory is actually to chart the fundamental interactions. I want a theory of all masses. I have to make mass of the all fundamental particles. It's called flame theory. If I'm lucky, that also will tell you a word about that theory. Unify the forces, for example, with this conformal symmetry that I was telling you about, make wonders. It's actually fantastic. Now, if you like string theory, then you know that in the past 10 years, there's the principle gravity gauge theory duality, which means gravity in higher dimensions linked to a gauge theory in lower dimensions. So we are an holographic projection of some gravitational plasticity, which is called ADS-CFT. And this can go in principle beyond even what is done so far. One off, I think, that we actually I'm interested in time traversal wormholes, not because I want to have interstellar version of that, but because they're cool on its own, and because there's a recent paper from Harvard where there's something interesting in that. And of course, we want to test with experiments. The picture to the right is from a recent paper where, for example, in charting fundamental interactions, we can now say that there is a new potential phase in QCD, quantum dynamics, when you have a large number of flavors, we'll save QCD. And this is pretty interesting because it allows, it opens up the theory of fundamental interaction to many more possibilities. But this is really my last, and it's just to, I mean, I'm often here that we need to steer research toward applied stuff. Let me say, not only candles, please. Why is it that? Shouldn't we invest only in applied research? Let's make this exercise 200 years ago. Let's think you did that. What would it come out? If you did that a few centuries ago, well, now you will have extremely power efficient candles. Very, damn good candles. But you will not have the electric power grid. You will not have positron emission tomography. Good luck with the cancer in your brain. You will not have internet. You will not have no computer, therefore not even science related to that. And above all, no smartphones. I mean, how the hell you will live without smartphones, right? Few of you knows that actually the screen of the smartphones were invented. That's why they're cheap, right? Otherwise, Steve Jobs will make even more expensive. Not only 1,000 euro for a next phone, it will be 10,000. So, only curiosity-driven research and team research brings to discoveries which you never ever thought would exist. University are places like that. I know that many of you bias to that, but I need to say, fine. Just leave you with Richard Feynman quote. Thank you.
Thank you so much for this tasting menu from the table of physics and a great lecture. Now, we have time for maybe 1 or 2 or 3 questions, should there be any. Yeah?
I have a somewhat not provocative, but
Please
question.
take it off.
So when you had the slide with this, defining fundamental is well defined, makes sense. But what's your proof or indication that the universe has to be fundamental in this sense? Yes? I mean, does it have to be?
Well, actually, yeah. So, because we can in principle follow the history of the universe all the way from the beginning. Now, an actual theory of nature should be able to do that.
But it doesn't need to be fundamental, right? In your definition.
Well, again,
it could be a different length scale, it could be really completely different physics.
But that's not what we see, right? In practice, it's
Not yet, right? I mean,
No, but I mean, it's. But again, the question is when you say, let me put the argument another way. Since I can devise theories which are fundamental, so I can actually differentiate them. I can test on whether the universe is a fundamental theory. So let me put it in a bit more pragmatic way. So I can differentiate theories mathematically according to the degree of fundamentality, so I can test it. That's what I love to do.
Anybody else? Well, there's some more good news, because after this lecture, what you ought to do is basically look to your left. Then there's a staircase, walk up, and there's a room exactly upstairs where there will be food, drinks, and occasion to discuss with Francesco and others here. So once again, Francesco, thank you, and a little reward is in place. Here you go. Thank you. See you upstairs.